We're off to chapter 8 here. Off to chapter 8, which this then should be exam 3 stuff we're off to here, I think. So we're going to talk about atomic masses in this table, in this chapter. We're also going to be talking about percent composition by mass, empirical and molecular formulas. So let's get into it here. So atomic masses are based on obviously the number of protons, electrons, and neutrons there are. Atoms are extremely small, so clearly you can't just kind of pick one up and put it on a balance. And when we talk about atomic masses, we are talking now about a lot of times the number that we see on the bottom of the periodic table there. Those are the atomic masses of all the elements. We will also talk about in this chapter another sort of version of that number, which is sometimes referred to as molar mass, which is just a little bit different in terms of how we use it. So a lot of times in chemistry, when we can't really measure something directly, a lot of times what they will do is pick something to use as a standard. So what they picked for atomic masses was an isotope of carbon, which is the carbon-12 isotope. And the carbon-12 isotope has a mass of exactly 12 AMU. AMU is an atomic mass unit. It is a unit that, frankly, we don't use all that much. We do use it when we talk about atomic mass. We don't use it a lot in the calculations. As we'll talk about in this chapter, and as I mentioned a second ago, we use kind of a more commonly used unit, which is molar mass, which is more applicable in our situations because it deals with grams rather than AMU. But we'll talk about that in just a bit. So basically, they used the carbon-12 isotope, which has 6 protons and 6 neutrons. And they sort of measured everybody in comparison to that carbon-12 isotope and said, like, hydrogen's only about 8% as big as the carbon-12 isotope. So they did a bunch of calculations to come up with really the atomic masses that we kind of see on the periodic table. So for example, as I just mentioned, something like hydrogen is about 8.4% as massive as carbon-12, and that is 8.4% converted into a decimal times 12, gives us a atomic mass for something like hydrogen of 1.008 AMU, which is kind of what we see on the periodic table when we look at it. We can find other atomic masses, obviously, from the periodic table, and one sort of conversion that we use for that is, for example, hydrogen 1.008. What we could say is there are 1.008 AMU in an atom of hydrogen. So that is sort of one way that you could kind of pull the numbers off the periodic table. In general, when we use atomic mass and later when we use molar mass, the typical rule is about 4 significant figures is usually what you pull from the periodic table. Depending on your periodic table, it may have a lot of numbers underneath each of the elements, or maybe not so much. But usually for calculations, if you go to the periodic table and pull off that atomic mass, or again, the molar mass later on, we do use it, and usually about 4 significant figures. So when we look at something like carbon, for example, what we actually see underneath carbon is actually 12.01, which means it is 12.01 AMU per atom. And you might say to yourself, well, if carbon was used as sort of the standard isotope and it had a mass of 12, why do we see sort of 12.01 when we look under the carbon? And the reason that we do see that is what we are actually looking at when we look at the periodic table is what is sometimes referred to as the average atomic masses, although most people don't call it that, they just call it atomic masses. But what it is an average of all the naturally occurring isotopes for that particular element. So every element will have a certain number of naturally occurring isotopes, and sort of the combination of all their masses together is how we get those up on the periodic table. There's actually sort of a formula that you can use to calculate atomic mass using AMU. And if you wanted to calculate the atomic mass of an element in AMU. You basically take the percent abundance is sometimes referred to of the first isotope, and you times it by the atomic mass of the first isotope. And then what you do is actually add it. So not multiply or anything like that. You actually would add it to the percent abundance of the second isotope times the atomic mass of the second isotope. And then basically you would continue that pattern depending on how many naturally occurring isotopes. So a lot of times you may be given like, hey, this isotope has a relative abundance of 22%. The other one has a relative abundance of 70 some odd percent. And when we add up the percent abundance or relative abundance is sometimes referred to, the percentages should add up to 100%. That means you have all the naturally occurring isotopes. If you add up the percentages and they don't equal 100%, then you are missing an isotope somewhere along the way. So this is the way that we sort of calculate the atomic masses that we see on the periodic table, once again, based on all those naturally occurring isotopes. So if we look at carbon, for example, carbon really has kind of two isotopes. It has kind of carbon-12 isotope and the carbon-13 isotope. And the carbon-12 isotope occurs about 99% of the time. The carbon-13 is about 1% of the time. And if we wanted to calculate the atomic mass of carbon, we would use these numbers. By the way, we would just quickly look at the percentages, and they do add up to about 100%. So we know we got pretty much all the naturally occurring isotopes. In this case, we would take the first isotope, which is our carbon-12, and we would convert it into a decimal, the percentage. You could do that by moving decimal place 2 places to the left, or divide it by 100, which will move it for you 2 places to the left. We times it by the atomic mass of the carbon-12 isotope, which is 12. We then again add it to the percentage of the carbon-13 isotope, which is the 1.1% converted into a decimal, times the atomic mass of our carbon-13. And if we do that, we will get something like 12.01 AMU, which is what we do see underneath carbon. It's really a combination of both the carbon-12 isotope and the carbon-13 isotope's mass, and we kind of use that average mass of both of those as the atomic mass for carbon. Question on that calculation there. It is important to remember that these are really just average values, which means that if you could like pick up a carbon sort of atom, if you will, and put it on a balance, you will never find one that has an atomic mass of 12.01. You would either find one that is a carbon-12 isotope that has a atomic mass of carbon-12, or you would find one that is the carbon-13 isotope that has the mass of carbon-13. Any questions on that there? All right, so why don't you try one here, an isotope that was 70.5% abundant with an atomic mass of 117.80, while the other naturally occurring isotope has an abundance of 29.5% and an atomic mass of 120. Calculate the atomic mass of this mystery element here in AMU. So see what you come up with. All right, let's take a look. So again, a couple of things we want to look at, which is first off, we have the percent abundance of these two isotopes. We just want to quickly take a look at the percentages, and they do add up to about 100% there. So that is good. Again, if they didn't, you would definitely be probably missing something, and you would have some other way to do it. By the way, if we were missing a percentage and we had the other percentages, we could add up the percentages, right, and subtract from 100, right? And that will tell us, you know, what the missing percentage would be. So we're going to figure out the atomic mass here by taking the first isotope, which is this guy. I'm going to convert it into a decimal. So we're going to move the decimal place 2 places to the left, or again, you can divide by 100 to do that. We're going to times it by the atomic mass of the first isotope. We're then going to do the same thing for the second percentage. We're going to divide it by 100 or move the decimal place, and that will get us 0.295 times our second isotope's mass, 120.85. And if we do all that good stuff there, about 118.7 AMU in this case, yeah. Which I made it up, but if we look on the periodic table, it looks like we might be talking about 10 there. Yeah, that's 118.7. Bless you. Any questions on that calculation there? So again, this is essentially how we do the calculation to figure out the atomic masses that we do see on the periodic table. Okay. So atoms are very tiny masses. So atomic mass unit in its equivalent form to a gram, as you can see, is 1.66 times 10 to the minus 24 grams. So 1 AMU is a very small amount of grams. All right, so we talked about that. So we can do and use atomic masses in AMU as conversion factors. And as I said, we probably won't do a lot of this, and you really don't do a lot of it in chemistry too much using the AMU sort of version. But again, if we were going to try to figure out the mass in AMU of 431 atoms of carbon, we would use our atomic mass from the periodic table as a conversion factor. So we could say there are 12.01 AMUs in an atom of carbon, or we could say in an atom of carbon, there are 12.01 AMU. So we really could use it as a conversion factor, and that's what we did here. We took the 431 carbon atoms, we put atoms of carbon on the bottom so they cancel. We basically multiplied the top, and we end up with 5176 AMU would be the mass there of 431 carbons. And obviously you could use the conversion on the other page if you want to know how many grams that was, kind of going a long way around it to figure it out. Another one here, if we look at aluminum, and if we look underneath aluminum on the periodic table, it will say 2698. So once again, one version of that, we could say 2698 AMU in an atom. Or an atom is 26.98 AMU. So once again, using that as a conversion factor here, the atoms of aluminum will cancel. Multiplying our 75 times our 2698 ends up with 2024 AMU. This is similar to how we do calculations, but we do use molar mass, which we're going to talk about here in just a second. And molar mass is numerically equivalent to what we see on the periodic table for atomic mass. It just has different units of grams per mole, which makes it a little bit more useful for us, because a lot of times when we do go to weigh something out, it's in the units of grams. So a lot of times when we do calculations, molar mass is really kind of the version that we use from the periodic table rather than AMU, which, you know, if you go to a scale, it doesn't really say AMU on it, but it does say grams. Any questions on AMU per atom conversions there? Okay. All right, here. Let's see. Maybe I could get it to go. Let's see. All right, so let's talk a little bit more about some useful sort of conversions, and that is molar mass and Avogadro's number. So we'll start with Avogadro's number and the mole. So in chemistry, we do have a sort of value that we use a lot, which is a mole. And the abbreviation of a mole is MOL, as you can see there in the middle. They had abbreviated it some way, so they got rid of the E. It is important, though, that when people see that MOL abbreviation, sometimes a lot of people jump to the conclusion that it is molecules, but it is not molecules. It is moles. So that's a very common sort of mistake that people make. They see the MOL and think molecules rather than moles. So keep that in mind as you go through it. But what does a mole represent? A mole represents really a certain amount of something. So in life, we have a lot of words that mean a actual number. If we have a pair of something, right, that means that you have 2. If you have a dozen of something, that means you have 12. If you're old and you have a gross of pencils, that's how they used to call them. It's 144 is what a gross represents. So we do have these names that sort of represent a numerical value. And in chemistry, the mole is really that sort of name that we use. And 1 mole of anything will equal 6.022 times 10 to the 23, which is known as Avogadro's number. And as we will see, the units of Avogadro's number are different and can be different. We could have them being atoms, which is a common unit. They could be molecules. They could be particles. They could be pizzas. They could be shoes, whatever it may be. Although you do come across the occasional pizza in chemistry, but most of the time it is going to be atoms and molecules, which are the most common units that we associate with Avogadro's number. So 1 mole of anything, just like a dozen of something represents 12, a mole of something in chemistry represents 6.022 times 10 to the 23. Which, as I mentioned, is pretty much Avogadro's number here. And we use Avogadro's number really as a conversion factor. We use it to convert between moles and atoms or moles and molecules. So very commonly, we use this as a conversion factor to go between moles to atoms or molecules. And backwards. And we could use it as a conversion factor like so. Obviously, if you have moles, you would multiply by Avogadro's number. And that would give you atoms. And if you had atoms or molecules, you would divide by Avogadro's number. And that will get you moles. So 1 mole of hydrogen would have 6.022 times 10 to the 23 atoms of hydrogen. 1 mole of carbon would have 6.022 times 10 to the 23 atoms of carbon. 1 mole of water would have 6.022 times 10 to the 23 molecules of water. We use molecules for water because it is a molecule, but for any individual element, we use atoms typically. So again, that's why those units kind of change, but it is the same number. And for any of those relationships, we could write 2 conversion factors. Once again, we could say 1 mole of hydrogen, 6.022 times 10 to the 23 atoms. And we could reverse it, 6.022 times 10 to the 23 atoms of hydrogen would give us 1 mole of hydrogen. So any of those relationships you could use Avogadro's number with. Anybody from the periodic table by itself, any element, which then it would be atoms for Avogadro's numbers units. And you can use it for any molecule or compound, and it would be molecules as a unit that you would use. Now, sometimes people go crazy with Avogadro's number. They want to use it in every calculation because, well, frankly, you remember that number and you feel like you should use it in every calculation because it makes it more chemistry-like, I suppose, but you should not do that. So you really should only use Avogadro's number if you are given a number that's in atoms or molecules, or you're really asked to calculate something that needs atoms or molecules. So if there's really no mention of atoms or molecules, you should not use Avogadro's number. Any questions on that there? Now, Avogadro's number, like I said, does represent a certain amount, and we use it as a conversion factor. Again, just like a dozen means you have 12 oranges. Now, we just talked about atomic mass and AMU from the periodic table, but really a more convenient sort of unit that we pull from the periodic table. And it really is the same number as we saw with the atomic mass, is what is sometimes referred to as the molar mass. And the molar mass has units of grams per mole. And the molar mass is really how many grams there are per 1 mole of a substance. And numerically speaking, the conversion factor between AMU and atom and grams to moles, it actually comes out to be in the same number that we see on the periodic table. So just like when we went to the periodic table and we saw that there was 1.008 AMU in an atom, we could go to the periodic table and pull that same 1.008 number off underneath hydrogen and say that there are 1.008 grams of hydrogen and 1 mole of hydrogen. That means that basically the molar mass of hydrogen is 1.008 grams per mole. Molar mass is always this way. The number always stays with the grams part, and it's always 1 mole. So number always stays with the grams part, and it's always 1 mole. We could do that from anybody on the periodic table. If we had carbon, there would be 12.01 grams of carbon and 1 mole of carbon, which means the molar mass of carbon, 12.01 grams per mole. We also could do it for things like, say, water, for example, which is not just an element by itself. In 1 mole of water, we basically would have 18.02 grams of water. And we get that by basically adding up all the parts. So water, there are 2 hydrogens, each from the periodic table as 1.008 grams per mole, plus 1 oxygen from the periodic table, that is 16 grams per mole. And that gives us our 18.02 grams per mole as the molar mass of water. So when you go to calculate the molar mass of a molecule or a compound, you basically just go to the periodic table, you add up all the parts that are there, and that would be how many grams there are per 1 mole of that particular substance. Question on that there. We use this like a conversion factor as well. So we could say, again, for water, that there's 18.02 grams per mole for water. Or you could flip it around and do a mole of water would be 18.02 grams. So again, we really use molar mass as a conversion factor, and molar mass is our conversion factor to go between grams to moles and back. So if you've got to do that conversion, take something from grams to moles or take something from moles back to grams, periodic table, molar mass is what you want to do. Once again, you usually take 4 significant figures for each element when you're pulling off the numbers. Any questions on that there? Now, we know that there is 1.008 grams of hydrogen and 1 mole of hydrogen. There would be how many hydrogen atoms in 1 mole? It would still be Avogadro's number. So that is how they all tie to each other. Same thing here. There's 18.02 grams of water and 1 mole of water. And 1 mole of water would have how many molecules? Yeah, I would still have Avogadro's numbers worth of molecules. So that is the relationship of how all those things sort of tie together. And obviously you can convert from one to the next. Any questions on that there? Molar mass and converting from grams to moles, almost one of the most important calculations that you learn in chemistry. You use it a lot in a lot of different places throughout chemistry. So definitely not like this, it will go away. All right, so that is the relationship there between AMU and grams, in case you're curious. All right, so let's talk about this here. As I mentioned, we have basically kind of two conversion factors, Avogadro's number, which is what we use to go from moles to atoms or molecules. And we have our molar mass, which we use to go from grams to moles or moles back to grams. So let's do some here as a practice here. All right, how many moles of helium are there in 5.46 moles of helium? If you look at the periodic table where helium is sitting, it will say 4.003 underneath it. So give it a go, see what you come up with. Okay, let's take a look. So first off, what we want to look at is sort of really the conversion that we're doing. We have grams and we want to end up with moles. So we want to go from grams to moles. So the first thing we want to think about, do we need to use Avogadro's number here? The answer is we do not. There's no mention of atoms, right? There's no mention of molecules. So you do not need Avogadro's number. What we do need and what we use for this conversion to go from grams to moles is the molar mass. And the molar mass, once again, comes from the periodic table. And when we pull that number off the periodic table, it means the molar mass of helium is 4.003 grams per mole, which we could use really as a conversion factor. Again, we could use a showing dimensional analysis, 4.003 grams of helium per mole of helium, or a mole. So we're going to start with our grams, 5.46 grams of helium. We're just going to do a little dimensional analysis here. So we do want to actually take the grams and put them on the bottom so that they cancel. This will give us 4.003 grams per mole of helium. Once again, here the grams will cancel, and that'll leave us with 1.36 moles of helium. Significant figures really based off of the original number there, which was 3 significant figures as well. Question on that calculation. As a calculation, you do a lot. Grams to moles in chemistry for sure. Any questions on it? Okay. So why don't we try this one here? What is the mass in grams of, actually, let's do this one. Let's do one here first. What is the, what is the mass of 32.5 moles of CH4? So carbon is 12.01. Hydrogen is 1.008 there. All right, give it a go, see what you come up with in this case. Okay, let's take a look since we're getting to the end here. So once again, we want to think about our conversion. We want the mass. I guess I should have put grams there. Mass in grams. So we're looking for grams and we are given moles. So once again, we want to go from moles in this case, 2 grams. It is the molar mass from the periodic table that's going to allow us to do that. In this case, though, we do have a molecule here that are a compound. So we basically just add up all the parts to it. So the molar mass of CH4 would be, there's 1 carbon from the periodic table, that's 12.01. There are 4 hydrogens, each from the periodic table is 1.008 grams per mole. And if we add all that together, we get a molar mass for carbon CH4 of 16.04 grams per mole. Remember, we could use that as a conversion factor where the grams are up on top and the moles are on the bottom, or if we need to flip it, moles up on top and grams on the bottom. So we'll start with our 32.5 moles of CH4. We want the moles to cancel, so we do want the moles from our molar mass on the bottom. Grams up on top. Remember that the grams stay together with the number. Moles will cancel, and we will end up with about 521 grams of CH4 in this case. Again, really based off of that right there, 3 significant figures. Any questions on that calculation? So these type of calculations going from grams to moles or moles to grams is a very, very common calculation that you need to be able to do a lot. And again, it's the periodic table molar mass that allows us to do that. Any questions? All right, we'll lay it up there